my name is Rick Avila, and today I'll be talking about improving CT lung cancer screening through calibration phantom and software innovations. So as we all know, early detection of lung cancer is absolutely critical for survival. The 5-year survival rate jumps up significantly if we detect things as small as 5 millimeters or 6 millimeters. But in order to be able to do that, we need to CT image 6 millimeter or 5 millimeter objects like these solid lung nodules you see here. And a really small change in diameter or volume can result in a big volumetric change. So it's really important that we get the imaging right. We're working with very few pixels, and it's important that we get the imaging right and highly calibrated so that these diameter measurements or volume measurements are done with high precision. And for that, we need to consider that the quality of a CT image degrades significantly in some scanners as you go out from the center of the scanner. So the center of the scanner is going to be generally the highest quality. And as you go 50, 100 millimeter, 200 millimeters out from isocenter, you get worse and worse quality on some scanners. For example, here, this is a machine on the left where you're going to see a nice thin slice. This is looks like a slice from a loaf of bread. But on another scanner, if you ask for similar performance, you might get this kind of basically bowed out shape, and it's not a normal looking slice at all. So your results can vary quite a bit depending on what scanner and what protocol you're actually using. Now, we've been documenting over the last 15 years large numbers of issues in CT scanners, including biases in Hounsfield units, the density numbers from CT scanners, as well as spatial warping and many other things. The biggest thing we saw was that we saw spatial warping on the order of 44% when we put phantoms on the chest of patients. These spheres should not have changed in size at all, yet we saw changes of 44% on the same model at different locations. And we've seen this clinically. This is time 1 on the left. It's time 2 from Mount Sinai. They got a case with this type of scanner, and and you can see that this was referred for biopsy. But it turns out that this is not growth of a nodule from this time point to this time point. This is actually just spatial warping of a CT scan due to the scanner itself. So fortunately, this was caught and the biopsy wasn't done, because that would have been unnecessary. Now, we've built phantoms like table phantoms and other things where we put them in these types of scanners, and we see the spatial warping gets worse as you go out to the periphery. And we've even gone as far, because people don't believe us, despite how much we say it, gone as far as measuring this out to the periphery. And the blue dots are on this 16 slice scanner using a helical acquisition mode, which is really the only mode you can use when you're doing a breath hold scan. And then the orange dots are when you do step and shoot. So you can see the tightness of the samples, the volume measurements when you use step and shoot versus when you use helical scanning. And this represents a 33% change in volume of these 6 millimeter by 6 millimeter diameter and height cylinders that you see here. So we definitely have a major problem here with this type of scanner, and it really shouldn't be used for lung cancer screening, especially for large patients. But I think the more troubling thing here is that we first reported this in 2011 in a major clinical trial, and it took over 3 years to publish these results, resulting in a JMI 2016 paper. And then I've made numerous presentations every year for the last 10 years. Yet even today, FDA approves these model scanners for lung cancer screening. AAPM provides screening protocols for these scanners, as you can see on the right. There's no mention of these scanners as having issues in numerous lung cancer screening guidelines, and numerous medical physicists continue to deny that spatial warping exists in 16 slice scanners, as we've been reporting. So basically, after 10 years of studying and reporting on this, it's really long past time for the community to accept that this major problem happened and that global image quality monitoring needs to be updated and running continuously, so image quality lapses of this magnitude never happen again. That's the hope, right? Now, the way we solve this at the company I run, Acumetra, and in conjunction with the RSNA and QIW, Quantitative Imaging Biomarkers Alliance, is we've developed a low-cost phantom that can measure fundamental properties of the acquisition system from the center of the scanner out to the periphery. And we build a 3D mathematical model based on this information, a mathematical model of the acquisition system. And it's all automated. You just scan the phantom, upload it to us, and you get back a report within 5 minutes. We build that 3D model using what we call, this is a little technical, but a Gaussian point spread function. This is a mathematical way of representing resolution. And once we have that information, we can experiment and build any images of what objects would look like in a scanner where we have that resolution information plus other things. And we produce visualizations like this to show what it would look like if you went on a future generation scanner with a certain object versus you went to the absolute limit of what our requirements suggest. So we've done lots of supporting studies on this. We have a recent study that just completed showing very high quality, indicating that we have very high quality, but there are no accepted standards that we can compare against for measuring 3D resolution. This is just a major, major problem. And we've also shown over time, these methods, when scanned every 3 months or over a year and a half here, are very stable and really quite remarkable in terms of their stability. Now we have 115 CTLX1 and CTLX2 phantoms distributed around the world, thanks to the Prevent Cancer Foundation grants and their grants. And numerous countries and organizations are now adopting this. So we've got a global network in place right now, which is awesome, running on the cloud. We've got the FDA, medical physicists at the NIH. We've got Stephen Lamb and his group putting out recommendations to use these tools, and we're delighted with the adoption around the world. We have a new phantom that better supports radiation dose versus image quality studies. And you can see here, it's a water fillable phantom with these things that look like hydration packs. This one's packed here with those water packs. And we can insert objects in it that look like simulated objects that look like nodules into the phantom, and people can check their software with it, the volumetric software, and make sure it's high quality as well. We put out some COVID-19 CT imaging guidance based on all the work we've done and the scans that we've analyzed over the years. We've actually analyzed over 1,400 CT scans from around the world. And because of that, we can now put out recommendations on which recon kernels work better for lung imaging, as you see here for COVID-19. We're working now, and Chuck Hatt will talk about this in his intro to the next panel, how we're coming up with a new guidance that will combine lung cancer screening and COPD, and will give guidance on how to acquire images for both those major diseases. Now, what can we do with quality information once you use these phantoms? Well, first thing is we can, in the future, provide precision follow-up times, where if we know the baseline diameter of the nodule, and we know the precision of the measurement instrument, the scanner and the protocol, we can look at how much time would be needed for different volume doubling times, as you see here. And 90 days might still have too much overlap, so we might set it to be 120 or 150. Again, one of the things you can do once you understand the precision of your measurement system. Another thing we can do is look at the trade-off between radiation dose and resolution. And here you can see on top a scanner that as you lower radiation dose significantly, the resolution stays the same, but the noise goes up. That's what you normally expect. But on another scanner, if you do the same kind of thing, The resolution is lost, but the noise stays more stable. Well, that's radically different behavior that sites don't know about unless they have a phantom and can do image quality checks and radiation dose checks as they modify protocols for different size patients. We also have ways of measuring the software of systems by inserting these small ellipsoids inside of phantoms. And we've seen some issues in different commercially available software in terms of the biases and the precision of those measurements. Another thing we can do is if a site has two different model scanners and they want to know, can they scan a patient on one at time one and on the other at time two, we can look at the image quality metrics that we have and align them better. So here there's different scanners colored in gray, orange, and blue. And you can see they're quite a bit different in resolution. But if we were to modify those protocols and bring them closer, both in resolution and on the right with noise, we might be able to lift the restriction that the patient has to be scanned on the same machine each time. That's a major limitation. It's a real problem for clinical sites. And with these tools, you can do that. And then more imaging reconstruction on CT scanners is more and more using AI. And that's going to create a lot different, a lot of potential differences in how reconstruction basically modifies those images. Not every innovation, though, is going to be for the better, just as we saw with those 16-slice scanners back 10 years ago. So we need a global image quality safety net, as we have now, to make sure that the quality of these images, as these new innovations come in, stays high. So in summary, we have now a global network of using a new low-cost CT calibration phantom, the CTLX-1 and the CTLX-2. We have 115 phantoms distributed around the world, and those sites can now quickly verify their CT image quality. And not only that, but they can optimize and they can share their crowdsourced protocols for CT lung cancer screening. And again, Chuck will talk about an effort that I'll be inviting a whole bunch of people to soon to look at guidance on protocols for both lung cancer screening and COPD. Now, it's important to recognize that these types of phantoms produce 3D mathematical models, and those models then can be used to predict performance for different clinical applications. But the more exciting thing to talk about here for this panel is going to be the potential clinical uses of CT image quality information, such as setting more precise lung cancer screening at follow-up times, doing better nodule volume growth or doubling time estimation, and also putting error bounds on those estimations, optimizing both radiation dose and CT image quality for nodule detection and measurement, enabling sites to use different but calibrated CT scanners and protocols for follow-up scans, establishing and updating image acquisition recommendations in real time with massive amounts of data like you see with this network that we have. And then finally, maintaining a global safety net for catching issues when scanner vendors deploy new CT innovations like artificial intelligence, and there'll undoubtedly be many, many other innovations coming. Finally, it's really important that we recognize that there are no accepted methods for measuring CT resolution. And thus, even though we have a study right now that is indicating our CTLX-1 data is both accurate and reproducible, we are having difficulty proving it because there is no gold standard. So if I could leave you with one thing at the end of this talk is the absolute critical importance of establishing a worldwide 3D CT resolution standard so that clinical sites can verify that the scanners they've purchased achieve those results that the manufacturer provides, and studies and research can document the quality of their scans, at least in terms of 3D resolution. So that's the story. Thank you very much. I appreciate your time.